light enough to accelerate quickly, strong enough to survive the laser bombardment without vaporizing, large enough to catch sufficient photons, small enough to not be unmanageable. And it needs to maintain its shape to micron-level precision, while being blasted with more energy than any material in history has been asked to withstand. Then there's the problem of aiming. The spacecraft would accelerate from 0 to 60,000 kilometers per second in 10 minutes. Keeping a laser beam focused on something that small, moving that fast, from a planet that's rotating, requires pointing precision that makes threading a needle while blindfolded seem trivial by comparison. The slightest deviation and you're not pushing the sail anymore, you're just heating random patches of space. Assume you solve all that. The probe reaches cruising speed and begins its 20-year journey. Now it faces a different hazard, the interstellar medium. Space between stars isn't empty. It's filled with hydrogen atoms, dust particles, cosmic rays. At 20% of light speed, colliding with even a single grain of dust releases energy equivalent to a small explosion. The probe would be sandblasted by atoms, each impact carrying enough energy to damage sensitive electronics. You can't armor against this. Armor adds weight, and weight destroys the entire concept. You can't dodge the particles because you have no propulsion system capable of maneuvering at those speeds. You just have to hope the path is clear enough that the probe survives. 20 years pass. The probe reaches Alpha Centauri, screaming past Proxima Centauri at 20% of light speed. It has no brakes, no way to slow down. It gets one shot at gathering data during a flyby that lasts hours at most. Every instrument, every camera, every sensor has to work perfectly after 2 decades of exposure to cosmic radiation and high-speed particle impacts. But the real problem emerges when you try to send that data home. The probe is 4 light-years away, traveling away from Earth at 60,000 kilometers per second. To transmit data, it needs power, a lot of power. Radio signals obey the inverse square law. They weaken with the square of the distance. At 4 light-years, even a powerful transmitter becomes a whisper. The probe weighs a gram. Where does transmission power come from? Solar panels are useless at Alpha Centauri if the probe is moving away from the stars. Batteries capable of storing enough energy for transmission would weigh far more than the entire probe. The proposal suggested using the sail itself as an antenna, but that requires engineering precision that borders on fantasy. And even if you solve the power problem, you face the bandwidth problem. Transmitting a single high-resolution image from that distance could take months. Video would take years. The data return from a mission that cost billions and represented humanity's first venture to another star might be a handful of pixelated images arriving after years of transmission. Breakthrough Starshot acknowledged these challenges. The project was structured as a long-term research program, not an immediate mission. The goal was to investigate whether the concept was even feasible, to identify the technical barriers, to begin developing solutions. What actually happened was more sobering. The promised $100 million in funding largely failed to materialize. Research grants totaled in the hundreds of thousands rather than millions. The work that did happen revealed problem after problem with no clear solution. By 2024, the project had effectively gone dormant, with no official cancellation but no visible progress either. This doesn't mean the concept was wrong. It means the gap between what we can do and what we need to do is wider than anticipated, perhaps much wider. Other approaches exist, at least on paper. Nuclear pulse propulsion, where you detonate small nuclear explosions behind a spacecraft to push it forward. Fusion ramjets that scoop up hydrogen from space and fuse it for propulsion. Antimatter engines that annihilate matter and antimatter for maximum energy release. Generation ships that take centuries to make the journey, with multiple human generations living and dying en route. Each approach faces obstacles that make Starshot's challenges look manageable. Nuclear pulse propulsion violates international treaties and creates radiation hazards. Fusion ramjets require technology we haven't developed and may not work in practice because the interstellar medium isn't dense enough. Antimatter doesn't exist in meaningful quantities and would require more energy to produce than it would release. Generation ships require life support systems that function perfectly for centuries, and social structures that remain stable across dozens of generations. You begin to see why no serious proposal for crewed interstellar flight exists. The problems aren't just technical, they're fundamental. They emerge from physics itself, from the relationship between mass, energy, and velocity, from the speed of light limit that makes the universe enormous and our speeds comparatively glacial. Which returns us to the central question: if Alpha Centauri is effectively unreachable with any technology we can currently envision, does it matter that planets orbit there? Does the knowledge that worlds exist 4 light-years away change anything if those worlds might as well be 4 million light-years away, for all the difference it makes to our ability to reach them? In one sense, no. The planets remain remote, inaccessible, beyond the practical reach of human exploration for the foreseeable future. We can observe them from Earth. We can study their light spectra, measure their masses, estimate their compositions. But visiting them, landing on them, walking their surfaces, that remains science fiction. Yet in another sense, their mere existence shifts the calculation. Because now we know, not that we suspect or theorize or hope, but that we know for certain. Other worlds orbit other stars, and those worlds aren't scattered randomly through the galaxy at distances that reduce them to pure abstraction. The nearest ones are right there, close enough that light from their suns reaches us in the time it takes to complete an undergraduate degree. This knowledge creates pressure, technological pressure to develop better propulsion, economic pressure to invest in capabilities that might eventually enable such missions, cultural pressure to think beyond our solar system as the boundary of human civilization. The planets around Alpha Centauri are destinations now, not just points of light. And destinations create imperatives that mere possibilities never could. Human history suggests that when destinations become known, eventually someone figures out how to reach them. The Pacific Islands seemed impossibly remote until Polynesian navigators crossed thousands of miles of open ocean in outrigger canoes. Antarctica was unreachable until it wasn't. The moon existed for millions of years before 1969, but once we knew it was a place, reaching it became inevitable. Alpha Centauri's planets might follow that pattern. Not soon, probably not within our lifetimes or our children's lifetimes, but the knowledge that they exist makes them targets for future capabilities we can't yet imagine. Technology that would seem like magic to us, the way our technology would seem like magic to someone from the 1800s. The question isn't whether we should try to reach Alpha Centauri. The question is what we learn in the attempt. Because the technologies we develop trying to reach Alpha Centauri will transform everything else we do in space. Consider what happened during the Apollo program. NASA didn't just build rockets to reach the moon. They created integrated circuits, developed fuel cells, invented new materials, pioneered computer miniaturization, technologies that had nothing to do with lunar exploration, except that solving lunar problems required inventing them. And once invented, they spread everywhere. The same pattern would repeat for Alpha Centauri, but amplified. Any propulsion system capable of reaching another star system would revolutionize travel within our own solar system first. A spacecraft that could reach 20% light speed would get to Mars in minutes instead of months, to Jupiter in hours instead of years. The entire solar system would shrink to the scale of a long road trip. But propulsion represents just one category. Communications technology capable of sending data across 4 light years would handle every distance within the solar system trivially. Power systems that could operate continuously for decades without refueling would enable missions that current spacecraft can't attempt. Life support that could sustain humans for generations would make permanent space habitation straightforward. The knowledge gained would extend beyond hardware. Understanding how to navigate interstellar space requires mapping gravitational fields with precision we haven't achieved. Protecting against radiation in deep space demands materials and shielding we haven't developed. Maintaining systems across decades or centuries requires reliability standards we haven't met. Each of these challenges exists whether we're aiming for Alpha Centauri or just trying to build better satellites. But the Alpha Centauri goal creates urgency. It provides a concrete target that justifies investment in capabilities that would otherwise remain theoretical. This explains why NASA and other space agencies study interstellar mission concepts, even knowing they won't launch such missions soon. The studies themselves advance the field. They identify which problems need solving. They suggest which technologies deserve development. They create roadmaps that guide research in productive directions. Breakthrough Starshot demonstrated this principle despite its current uncertain status. The project brought together physicists, engineers, materials scientists to think seriously about light sail propulsion. Even if Starshot never launches, the work produced insights about laser arrays, ultra-lightweight materials, precision manufacturing at nanometer scales. Insights that apply to other projects, other goals, other missions. You're probably wondering whether any of this matters if we can't actually reach Alpha Centauri in any reasonable time frame. Here's why it does. The value isn't reaching Alpha Centauri specifically. The value is building capabilities that make reaching Alpha Centauri theoretically possible, because those capabilities transform what we can accomplish everywhere else. Think about the International Space Station. Nobody built the ISS because we desperately needed a laboratory in low Earth orbit. We built it because maintaining a permanent human presence in space requires solving thousands of small problems. How do you recycle water in zero gravity? How do you grow food without soil? How do you maintain equipment when you can't just order replacement parts? Solving those problems for the ISS created knowledge that applies to every future space habitat, whether on the Moon, Mars, or eventually in deep space. The ISS wasn't the destination. It was the training ground. Alpha Centauri serves the same function for interstellar capability. We don't need to actually send humans there to benefit from trying to figure out how we would send humans there. Which brings us to an uncomfortable question. If the real value lies in developing the technology rather than reaching the destination, why not just develop the technology without the expensive, probably impossible mission goal? Because humans don't work that way. We need concrete goals. Abstract capability development doesn't inspire the public, doesn't justify budgets, doesn't motivate researchers to solve hard problems. The moon landings didn't happen because NASA wanted to advance rocketry. They happened because President Kennedy set a specific goal with a deadline: reach the moon before 1970. That specificity created focus that general technological advancement never could. Alpha Centauri provides the same focus for interstellar capability. It's specific, measurable, achievable in principle, if not in practice with current technology. It gives researchers something concrete to aim for, rather than vague aspirations about advancing propulsion or improving efficiency. The planets orbiting Alpha Centauri strengthen this dynamic. Now we're not just trying to reach another star system. We're trying to reach worlds that might harbor conditions for life. That might teach us something about how planets form. That might show us examples of geology, weather, chemistry operating under different conditions than Earth's. Scientific motivation combines with exploration motivation. Both reinforce the engineering motivation, and together they create pressure to develop capabilities that transform space exploration generally. But there's another dimension to consider, one that extends beyond technology or science into questions about humanity's long-term future. Our solar system won't remain habitable forever. The sun will eventually expand into a red giant, engulfing Earth and the inner planets. That won't happen for billions of years, but it will happen. At some point, if humanity still exists, we'll need to leave. More immediately, various existential risks threaten our survival as a species. Asteroid impacts, supervolcano eruptions, nuclear war, pandemics, climate change. Some of these we might prevent or mitigate. Others we can't control. Establishing human presence beyond Earth provides insurance against planetary-scale catastrophes, but staying within our solar system only partially addresses this problem. A catastrophe that destroys Earth might also threaten Mars or the Moon or orbital habitats. They all orbit the same star, exist within the same gravitational well, share many of the same vulnerabilities. True long-term survival requires spreading to other star systems. Not because we'll need that capability soon, but because eventually, on timescales of thousands or millions of years, our descendants might need options we don't currently have. Alpha Centauri represents the first step in that multi-generational project. Not because we'll colonize it next century, but because learning how to reach it teaches us how to reach other stars. And reaching other stars eventually becomes necessary if humanity intends to survive indefinitely. This perspective transforms the question. We're not asking whether we can reach Alpha Centauri with current technology. Obviously, we can't. We're asking whether we should begin developing capabilities that might eventually enable such missions. Knowing the development itself creates value regardless of whether the mission launches. The answer seems clearly yes, because the alternative is accepting permanent confinement to one solar system, one planet, one basket for all of humanity's eggs. But accepting this answer creates new questions. How much should we invest in such long-term capabilities? What priority should they receive compared to more immediate challenges? How do we balance resources between solving problems on Earth and developing capabilities for leaving Earth? These questions don't have simple answers. Different people reasonably disagree about proper priorities, about how much attention humanity should devote to space exploration versus other goals. What's clear is that the discovery of planets around Alpha Centauri changed the calculation. Before we knew those planets existed, interstellar travel remained pure abstraction. Interesting theoretically, but disconnected from anything real. Now we know specific worlds orbit specific stars at specific distances. We can point telescopes at them, measure their properties, estimate their characteristics. They're not hypothetical anymore. They're actual places that exist whether we reach them or not. And knowing they exist creates pull. Psychological pull toward developing capabilities to study them more closely. Economic pull toward technologies that might enable such missions. Cultural pull toward thinking of humanity as a multi-system species rather than a planetary one. That pull won't translate into missions tomorrow or next decade. The obstacles remain formidable. The costs remain astronomical. The timescales remain discouraging. But pull accumulates over time. It influences research priorities, funding decisions, career choices. It shapes which problems seem worth solving, which technologies seem worth developing, which goals seem worth pursuing. The students studying aerospace engineering today grew up knowing exoplanets exist around other stars. That knowledge shapes their ambitions differently than previous generations, who could only speculate. Some of them will spend careers developing technologies that bring interstellar flight incrementally closer to feasible, and their students will build on that work. And their students will build further, until eventually someone looks up and realizes the impossible has become difficult. And the difficult has become expensive, and the expensive has become merely challenging. That's how impossible things become possible. Not through sudden breakthroughs, but through accumulated incremental progress across generations. Each generation pushing the boundary slightly further. Each advance making the next advance slightly easier. Alpha Centauri's planets provide the target that focuses this multi-generational effort. They transform interstellar flight from abstract concept to concrete engineering challenge. They create specific questions that demand specific answers. They turn "someday we might" into "eventually we will." Which means the real question isn't whether we can reach Alpha Centauri. It's whether we're willing to start the journey knowing we won't see the destination. Human history suggests we are. We plant trees we won't sit under. We build cathedrals we won't see completed. We invest in research that won't pay off for decades. We think beyond our own lifetimes when the goal seems worthy enough. Reaching other star systems seems worthy enough. Not because we need to next year or next century, but because the journey itself transforms us. Because the capabilities we develop enable achievements we can't yet imagine. Because the simple act of trying expands what humanity considers possible. The planets around Alpha Centauri wait patiently in the dark. They don't care whether we reach them. They'll continue orbiting their stars long after our civilization has ended. But knowing they exist changes us. It shifts our perspective from earthbound to starbound. It makes the galaxy feel less empty and more like territory waiting for exploration. That shift in perspective might be the most valuable thing Alpha Centauri gives us. Not a destination we can reach, but a horizon we can aim for. Aiming toward Alpha Centauri changes us even before we get there. Consider what happens when humanity collectively points towards something impossibly distant. The goal itself becomes less important than what we build while pursuing it. The Apollo program never aimed primarily at the moon. It aimed at demonstrating technological supremacy during the Cold War. But the technologies developed along the way, integrated circuits, computer miniaturization, advanced materials, transformed industries that had nothing to do with space. GPS satellites, weather forecasting, global communications. All downstream effects of chasing one distant goal. Interstellar flight follows similar logic. We won't develop the capability to reach Alpha Centauri by focusing exclusively on Alpha Centauri. We'll develop it by solving thousands of smaller problems that collectively make interstellar flight possible. Advanced propulsion systems that enable faster solar system exploration. Better radiation shielding that protects astronauts on Mars missions. Life support systems capable of operating for decades without resupply. Each advancement serves immediate practical purposes while incrementally closing the gap toward interstellar capability. This creates economic justification that pure exploration cannot provide. Congress won't fund a 70,000-year mission to Alpha Centauri, but it will fund technologies that reduce Mars mission costs, extend satellite lifespans, enable asteroid mining. Those same technologies push interstellar flight from impossible toward merely improbable. The psychological shift matters more than the technology. Previous generations grew up knowing stars were distant, unreachable points of light. Current generations know specific planets orbit those stars. Future generations will grow up seeing detailed images of exoplanet atmospheres, spectroscopic analyses of their compositions, maybe even surface features. That familiarity transforms abstract destinations into concrete places worth reaching. Think about how moon missions changed public consciousness. Before Apollo, the moon represented romantic abstraction. After Apollo, it became somewhere humans had walked. The transition from abstract to actual fundamentally altered how we think about space. Exoplanet discoveries around Alpha Centauri create similar transitions. Those worlds exist whether we acknowledge them or not. But knowing they exist changes how we think about our place in the cosmos. Proxima b orbits 4.24 light-years away. That distance hasn't changed, but our relationship to that distance has. Before we knew Proxima b existed, 4.24 light-years represented empty space between stars. Now, it represents the distance to a specific world with specific characteristics orbiting a specific star. The number stays constant, but its meaning transforms. This transformation drives technological development in unexpected directions. Material scientists working on better solar panels for Earth applications discover techniques applicable to light sails. Computer engineers developing AI for autonomous vehicles create algorithms useful for spacecraft navigation across interstellar distances. Biologists studying extremophiles in Earth's deep ocean inform models of potential life around Proxima Centauri. Progress in one domain feeds progress in another, until the accumulated knowledge base makes previously impossible things merely difficult. The timeline matters less than the trajectory. Whether we reach Alpha Centauri in 300 years or 3,000 becomes less relevant when viewed across civilization timescales. What matters is establishing trajectory, demonstrating that humanity is collectively moving toward interstellar capability rather than away from it. Each generation doesn't need to complete the journey. It just needs to advance further than the previous generation managed. Ancient civilizations understood this. They built cathedrals knowing completion would take centuries. They planted orchards knowing the fruit would feed their grandchildren. They invested in irrigation systems that would serve communities for generations. Modern civilization often forgets this long-term thinking, focusing on quarterly earnings and election cycles. Interstellar flight forces us to recover that perspective. You can't optimize quarterly returns when planning missions that span lifetimes. You can't campaign on promises that won't materialize for centuries. The very act of seriously pursuing Alpha Centauri requires adopting timescales that transcend individual human lives. That shift in perspective might prove more valuable than reaching Alpha Centauri itself. Because the real limitation isn't distance, it's thinking. We're trapped in mental models shaped by terrestrial experience, where destinations are reachable within lifetimes, where investments pay off before investors die, where problems have solutions discoverable by the people who encounter them. Interstellar flight breaks all these models. It demands thinking across generations, planning across centuries, accepting that the people who start the journey won't see its completion. This represents fundamentally different relationship with time, not better or worse, just different. Agricultural societies planted olive trees their great-grandchildren would harvest. Industrial societies built infrastructure their grandchildren would use. Information societies struggle to plan beyond next quarter's earnings report. Interstellar societies, if we become one, must think across timescales that dwarf individual human perception. Alpha Centauri provides focus for that thinking. It's not the only possible target. Other stellar systems might offer better scientific returns or more hospitable environments. But Alpha Centauri holds one irreplaceable advantage. It's closest. That proximity makes it the obvious first step toward broader interstellar capability. Success there validates techniques applicable to more distant systems. Failure there teaches lessons without requiring century-long mission times to other targets. The system's triple nature adds complexity but also opportunity. Proxima orbits roughly 13,000 astronomical units from the Alpha Centauri AB binary pair. That's 400 times Neptune's orbital radius. Vast by solar system standards, trivial by interstellar standards. A mission reaching Proxima could potentially study all three stars and whatever planets orbit them. One journey, multiple targets. That efficiency matters when each journey costs civilization's total resources. Proxima's flare activity complicates habitability but creates research opportunities. Those flares strip atmospheres from close orbiting planets. They create radiation environments hostile to Earth-based life, but they also provide natural experiments in atmospheric dynamics, magnetosphere interactions, radiation chemistry. Understanding how planets survive or fail to survive such environments informs our understanding of habitability throughout the galaxy. Proxima b likely isn't habitable in any sense humans would recognize. It receives too much radiation. Its atmosphere has probably been stripped. Its surface conditions likely preclude liquid water despite orbiting within the traditional habitable zone. But studying why it's uninhabitable teaches us what habitability actually requires. Each inhospitable world we characterize narrows the search space for genuinely habitable ones. The recent observations suggesting a planet around Alpha Centauri A add another layer. If confirmed, that world orbits a Sun-like star at roughly twice Earth's orbital distance. Too far for traditional habitability, but potentially interesting for other reasons. Gas giants at that distance might host habitable moons. They might have formed closer and migrated outward, clearing debris and creating stable orbits for inner rocky planets we haven't detected yet. They might simply represent another data point in understanding planetary system formation. Each discovery raises more questions than it answers. That's how science works. We don't discover final answers. We discover better questions. Alpha Centauri keeps providing better questions. What determines planetary habitability around M-dwarfs? How do planetary systems form around binary stars? What atmospheric compositions allow liquid water despite high radiation? How does stellar activity affect long-term planetary evolution? These questions drive research that improves our understanding of planets generally, not just those around Alpha Centauri. Every technique developed to study Proxima b applies to thousands of other exoplanets. Every model refined to explain Alpha Centauri's planetary system informs models of planetary formation everywhere. The knowledge compounds. The techniques generalize. The insights propagate. This creates practical value independent of actually reaching Alpha Centauri. Better understanding of planetary atmospheres improves climate models for Earth. Better radiation shielding protects astronauts throughout the solar system. Better propulsion systems reduce costs for satellite launches and deep space probes. The pursuit generates returns long before achieving the ultimate goal, which means failure becomes less catastrophic than you'd expect. Even if we never reach Alpha Centauri, the attempt drives technological development that serves other purposes. Ancient explorers who died searching for the Northwest Passage still advanced geographic knowledge. Early aviation pioneers who crashed still contributed data that made later flight possible. Failed interstellar missions would teach lessons that make subsequent attempts more likely to succeed. This reframes the entire enterprise. We're not betting everything on one impossible goal. We're using that impossible goal to drive systematic progress toward capabilities useful regardless of whether we achieve the specific objective. The journey itself justifies the investment. The destination provides direction, but doesn't determine value. That perspective allows longer timelines without feeling like failure. If reaching Alpha Centauri takes 500 years instead of 200, that's fine. The technologies developed during those centuries serve other purposes. The knowledge gained applies to other challenges. The cultural shift toward long-term thinking benefits civilization generally. The timeline extends, but the value accumulates continuously rather than paying off only at completion. This makes interstellar flight different from other grand challenges. Curing cancer either succeeds or fails. Building fusion power either works or doesn't. Reaching Alpha Centauri generates value throughout the attempt regardless of ultimate success. Every advance toward interstellar capability enables applications within the solar system. Every technique developed for generation ships applies to Mars colonies. Every breakthrough in closed-loop life support serves space stations. The pursuit itself drives progress independent of achieving the final goal. So when people ask, why Alpha Centauri? The answer isn't because we need to get there. It's because aiming there takes us places we couldn't reach otherwise. The destination focuses effort. The journey transforms capability. The attempt changes who we are as a civilization. And that transformation might be what matters most, not the specific achievement of reaching one particular star system, but the cultural evolution required to seriously attempt it. The shift from quarterly thinking to century thinking, from individual accomplishment to generational progress, from terrestrial perspective to cosmic perspective. These changes ripple through civilization in ways that transcend space exploration. You can't think seriously about interstellar flight without confronting human mortality, without accepting that the people who start the journey won't see its completion, without recognizing that your contribution might be developing one component that enables someone 3 generations later to solve the next problem. That acceptance changes how you think about everything, about legacy, about progress, about what makes life meaningful when your individual existence occupies such tiny fraction of relevant timescales. Alpha Centauri forces those confrontations. It demands we think beyond ourselves, plan beyond our lifetimes, invest in futures we won't witness. And in making those demands, it might teach us something more valuable than how to cross interstellar distances. It might teach us how to think like a civilization that survives long enough to become interstellar in the first place. Perhaps that's the real reason Alpha Centauri matters. Not because we need planets to colonize or resources to extract, but because attempting something this difficult forces beneficial changes regardless of outcome. Consider what happens when a civilization commits to century-scale projects. Investment horizons extend, educational priorities shift, research becomes less focused on quarterly returns, infrastructure gets built for descendants rather than shareholders. The entire cultural metabolism slows down in ways that might actually increase survival probability. Short-term thinking creates fragile systems. Quarterly earnings pressure, election cycles, fiscal years. These temporal frameworks optimize for immediate results at the expense of long-term stability. They encourage exploitation over sustainability, extraction over cultivation, consumption over preservation. But you can't think about Alpha Centauri in quarterly increments. The mission duration exceeds any individual lifetime by orders of magnitude. Success requires institutional continuity across multiple generations. Planning horizons must extend beyond anyone's personal stake in the outcome. That shift in temporal perspective might be more valuable than actually reaching the destination, because civilizations that can't think beyond immediate returns probably don't survive long enough to become interstellar anyway. The filters that prevent most species from spreading beyond their home worlds might be psychological rather than technological. Not, can we build the ships, but can we think far enough ahead to want to? Alpha Centauri provides that test. It demands we prove we can plan beyond ourselves, that we can invest in futures we won't experience, that we can value outcomes our grandchildren's grandchildren might witness. And passing that test changes everything else. Climate change requires century-scale thinking. Asteroid defense requires millennium-scale preparation. Avoiding technological self-destruction requires planning beyond election cycles. All the major challenges facing civilization demand temporal perspectives that Alpha Centauri forces us to develop. So maybe the mission succeeds even if the spacecraft never arrives. Maybe proving we can sustain a multi-generational project demonstrates the cultural maturity necessary for long-term survival. Maybe just attempting something this ambitious shifts how we think about time in ways that benefit everything else we do. There's historical precedent for this. Cathedral construction took generations. Medieval builders laid foundations knowing their great-grandchildren would complete the spires. That multi-generational commitment required cultural institutions that could maintain purpose across lifetimes. And those institutions shaped European civilization in ways that transcended any individual cathedral. The Apollo program lasted barely a decade, but transformed technological culture permanently. Not because we needed moon rocks specifically, but because attempting something that difficult drove systematic innovation across countless domains. The returns came from the pursuit rather than the destination. Alpha Centauri represents that pattern at maximum scale. The pursuit spans centuries. The challenges touch every aspect of technology and organization. The cultural shifts required to seriously attempt it might matter more than whether we ultimately succeed. Which brings us to something subtle about destinations versus directions. When you aim for a specific target, you either hit it or miss. Success is binary, but when you use a distant target to establish direction, you generate value continuously along the vector, even if you never reach the endpoint. Columbus aimed for Asia, but found America. The destination was wrong, but the direction proved valuable. Early aviation pioneers aimed for transatlantic flight, but generated insights that enabled all subsequent aviation. The specific goal mattered less than the systematic pursuit. Alpha Centauri works the same way. Maybe we never reach it. Maybe the mission fails. Maybe we discover something en route that makes the original destination irrelevant. But the direction, outward, beyond the solar system, toward other stars, that direction drives development regardless of whether we reach this particular target. And that might be enough, because the alternative isn't stay home and be comfortable. The alternative is stagnation, followed by extinction. Species that stop expanding eventually stop adapting. Civilizations that stop reaching for difficult goals eventually lose the capability to solve difficult problems. Comfort breeds fragility. Challenge builds resilience. Alpha Centauri provides perpetual challenge. Even with perfect technology, the distances involved prevent easy travel. Even with generation ships, the timescales exceed individual lifetimes. Even with everything working optimally, success remains uncertain enough to demand continued innovation. That's actually ideal. Easy goals don't drive sustained development. Once you achieve them, progress stops. But goals difficult enough to require multiple generations of effort create continuous pressure for improvement. The sweet spot isn't achievable in one lifetime, but potentially achievable if we keep trying for centuries, which Alpha Centauri is, close enough that reaching it seems physically possible, far enough that doing so requires capabilities we don't currently possess. The perfect distance to drive sustained effort without seeming completely impossible. And there's something poetic about that. Our nearest stellar neighbor sits just beyond reach. Not so distant we can dismiss it as irrelevant. Not so close we can reach it casually. Exactly far enough to require becoming something greater than we currently are. Like the universe placed a test just outside our doorstep. A challenge scaled perfectly to our capabilities, plus several generations of determined effort. Not impossible, but not easy. The ideal difficulty to drive growth without guaranteeing failure. Whether that's coincidence or something deeper remains unknowable, but the functional result is clear. Alpha Centauri occupies the precise distance that makes interstellar travel maximally difficult while remaining theoretically achievable. And that difficulty might be exactly what we need. Because easy goals don't change civilizations. Comfortable challenges don't drive transformation. Only by attempting something genuinely hard do we develop capabilities we didn't know we needed. Only by reaching for targets beyond our grasp do we extend our reach. And maybe that's the ultimate answer to why we should go. Not because we need to be there, not because resources or planets or knowledge await us, but because the attempt makes us better. Because reaching for the stars, even knowing we might never touch them, elevates us beyond what we'd become if we stayed comfortable. The cosmos offers no guarantees. Alpha Centauri might prove barren. The journey might fail. Everything we invest might generate nothing but expensive lessons. But those lessons themselves might be what saves us. The capabilities developed might be what prevents extinction. The cultural transformation might be what allows civilization to survive its own power. In which case, the mission succeeds regardless of whether the spacecraft arrives. Because the point was never really about reaching one particular star system. It was about becoming the kind of civilization capable of trying. About developing the long-term thinking, the institutional stability, the technological capability, and the sheer audacity required to attempt something this difficult. Those qualities matter far beyond space exploration. They're probably necessary for any civilization that survives contact with advanced technology. The filters that destroy most species might select specifically against short-term thinking, institutional fragility, and lack of ambition. Civilizations that can't attempt multi-generational projects probably can't survive the challenges that technology inevitably creates. Alpha Centauri tests whether we pass that filter, not by providing resources or destinations, but by demanding we develop the civilizational maturity necessary to attempt it. And in demanding that maturity, it might give us the one thing we truly need. Not more planets or more knowledge, but more time. The temporal perspective necessary to survive our own cleverness. Because that's the real challenge. Not building the ships or solving the physics or surviving the journey. It's thinking far enough ahead to want to. It's valuing futures beyond our own lifetimes. It's investing in outcomes we'll never witness. And civilizations that learn to do that might be the only ones that survive long enough to actually reach the stars. Which means Alpha Centauri offers something more valuable than any destination. It offers the question that determines whether we become something greater or remain trapped by our own short-sightedness. And how we answer that question, whether we seriously attempt the journey or dismiss it as impractical, might determine everything that comes after. The stars aren't going anywhere. They'll still be there in 1,000 years, 10,000, 1,000,000. But whether we'll still be here to reach for them depends entirely on choices we make now. On whether we can think beyond ourselves, beyond our lifetimes, beyond everything that makes thinking difficult but meaningful. Alpha Centauri sits there in the southern sky, neither approaching nor receding at any pace that matters to human timescales. A triple star system, 4.37 light-years distant, close enough to tantalize, but far enough to demand we become something greater than we are. The perfect test, the ideal challenge, the question that might matter more than any answer we could possibly give it. The question was never really whether we can reach Alpha Centauri. The question was whether we're the kind of species that tries. Every technological civilization faces this test eventually. The moment when comfortable expansion within a home system becomes insufficient. When the easy resources are claimed, the obvious destinations visited, the simple problems solved. What comes next determines everything. Some species probably stop. They build comfortable homes on comfortable worlds and optimize for comfort until something, resource depletion, stellar evolution, cosmic accident, ends them. They never develop the capabilities that might have saved them because those capabilities only emerge from attempting difficult things. Other species keep reaching, not because reaching guarantees success, but because the attempt itself transforms what's possible. They aim for targets beyond their grasp and discover their reach extends further than they thought. They invest in futures they won't witness and create legacies that outlast their individual existence. We don't know yet which kind we are. The verdict isn't in. But Alpha Centauri offers the test that determines the answer. Every advance toward interstellar capability, whether we ultimately use it or not, makes us more resilient. Better propulsion means faster response to asteroid threats. Better life support means viable off-world colonies. Better long-term planning means surviving challenges that require century-scale solutions. The capabilities themselves matter more than the destination that inspired them. And maybe that's the real gift of those distant worlds orbiting Proxima Centauri. Not that they exist specifically, but that knowing they exist changes us, makes the galaxy feel less empty, makes other stars feel less like abstract points of light, and more like neighborhoods we haven't visited yet, makes interstellar space feel less like an insurmountable barrier, and more like an ocean we haven't learned to cross. Humans crossed oceans before we understood ocean currents. We flew before we fully understood aerodynamics. We ventured into space before we'd solved the engineering challenges that made space travel routine. The pattern holds. The destination comes first in imagination, then in aspiration, then in capability developed specifically to reach it. Alpha Centauri follows that pattern. Today it's imagination, the worlds we think might exist there based on fragmentary observations. Tomorrow it becomes aspiration, the place we decide we want to reach even knowing the difficulty. Eventually it becomes capability, the technologies we develop specifically to make the journey possible. That progression takes time, probably more time than any of us have individually. But time scales differently for civilizations than for people. What seems impossibly long from a human perspective becomes merely challenging from a civilizational one. And civilizations that survive learn to think on civilizational timescales. The students studying aerospace engineering today won't build the ships that reach Alpha Centauri, but they'll build the ships that prove interstellar flight is possible. Their students will push the capability further, and their students further still, until someone looks up and realizes the impossible became difficult, the difficult became expensive, and the expensive became merely challenging. That's how species transcend their home systems, not through sudden breakthroughs, but through accumulated progress across generations. Each generation pushing slightly further than the last. Each advance making the next advance slightly easier. Each impossibility becoming slightly less impossible until it transforms into something merely hard. We're at the very beginning of that progression. The first generation to know planets orbit our nearest stellar neighbor, the first to seriously consider what reaching them might require. The first to face the choice between attempting something impossibly difficult and accepting permanent confinement to one solar system. How we respond to that choice matters more than whether we succeed. Because the attempt itself, the serious, sustained, multi-generational attempt, transforms us in ways that determine whether we survive long enough to become truly interstellar. And that transformation might be what the universe is waiting to see. Not whether we can build the ships, but whether we can think far enough ahead to want to. Not whether we solve the physics, but whether we develop the cultural maturity to sustain century-scale projects. Not whether we reach other stars, but whether we become the kind of species that reaches for them.